Now, today we will do the calculation of wavelength by de Broglie's formula. Alright, calculation of wavelength by de Broglie's formula when a potential difference V is applied across to it. Means I mean to say, suppose an electron is there, electron beam is there. We are applying a potential difference, that is V. Let us say V, we are applying. So the energy acquired by the electron is nothing but E into capital V. Energy acquired by the electron, isn't it? Electron beam is there. We are applying a potential difference. We are applying a potential difference across it. So the energy which is acquired by the electron is nothing but small e into capital V. Now definitely when it gains some energy, when it acquires some energy, the electron starts moving. Of course it is moving, but it starts moving with an increase of acceleration. It is of course moving, no doubt about it, but it is moving with an increased acceleration. What it is moving. So that is, it changes into energy, which is nothing but known as kinetic energy. We can say that because energy possessed by a body in motion is known as kinetic energy. Got it? Again I repeat, an electron beam is there, you are applying a potential difference across it. So it gains some energy, the electron gains some energy, and that energy, with the help of that energy, it accelerates, the electron accelerates and it moves. So the energy possessed by body in motion is what? Half mv square, we can say that, kinetic energy. Now we have to find the wavelength of that particular, what you can say, electron beam. You have to find out. So what you need to do? Now see here, that is EV. Now this V is potential difference. E is the electron, the charge on the electron. M stands for the mass of the electron. V is the velocity of the electron. We can say that. So small v, let me write small v is equal to 2e into capital V by m. Alright, see that 2e into capital V by m root over. We got it? Clear? Now next is we have seen it, lambda is equal to h by mv, small v. Lambda is equal to h by mv, that means 1 by v. So here we can write that is h by, that is mv. So v is nothing but this one is equal to this. Here 1 by v is there, mind it. Here this v is equal to root over of t 2e into capital V by m. See here, v is equal to. But here what is that? H by mv, that means 1 by v, mind it. Alright, so what it will be? Reciprocal of it. So it is nothing but, that is m by 2e into capital V. Is right? That is m by 2e into capital V. We can say that. So now if you simplify it, what will happen? This root m and here also root m into root m. So one root m, it gets cancelled. So what you will be getting? Root over of 2m e into capital V. Mind it, this V is your potential. This V is your potential, this V, and this V was small v was the velocity. Alright? Listen. So now h, the value is constant, 6.626 into 10 to the power minus 34 joules again. M, the mass of the electron, which is 9.1 into 10 to the power minus 31 kg. E is the charge on electron, which is 1.602 into 10 to the power minus 19 coulomb. And V is the potential difference, which is only varying. Now when you will put this value, the value of H, the value of M, the value of E, then ultimately what you will be getting is that lambda is equal to 1.226 into 10 to the power minus 19 by root over of capital V. Mind it. That is, let me write it a big one so that you, otherwise you will think it as small v. It is not small v, it is capital V. Okay, again I write 1.226 into 10 to the power minus 19 by root over of capital V, that is potential. I am saying you potential. When you put the value of H, M and E, when you put it, you will be getting this as lambda is equal to this much what? Meter. Definitely it's SI unit, that is nothing but meter. 1.226 into 10 to the power minus 19. So this is the wavelength calculated by de Broglie, we can say. So it is also said to be as de Broglie's wavelength. Got it? Now we have got numericals upon it. We will do it later on that particular one. Now coming to, that is the next principle. Now de Broglie's we have finished up. Now one more was there, You know it, that is Heisenberg's uncertainty principle. We can say that Heisenberg's uncertainty principle. What I said? Heisenberg's uncertainty principle. Alright? Heisenberg's uncertainty principle. Very, very important. Now, what do you mean by this particular? Why it is uncertainty? Listen very carefully. Alright? The concept will going to change after this. Now, see, when a car is moving on a road, when a bus is moving on a road, alright, when the planet is moving in an orbit, they are having a particular trajectory, means path. They are moving on their own path. Alright? So, when these objects are moving on their path, we are able to know the position of that particular object. We are able to know the path of that particular object. From the path, we can also calculate, that is nothing but velocity. We can, and as a result, we can calculate the momentum. Mass into velocity, we can say we can calculate the momentum. That means we can know the position. Like suppose a bus is moving. Now we can say, see, the bus is moving. So we can identify the position as well as we can identify the path, on which path it is moving. Yes, we can see the path or not, because it's moving on the road. So in this way we can know the path from which we can calculate the velocity. Yes, from the speedometer. We can't calculate the velocity. Yes, we can calculate the velocity. As a result, we can calculate the momentum, that is mass into velocity. That means for macroscopic object, we can calculate the momentum as well as the position. Alright. But suppose when an electron is moving, now how will you know the electron is moving? What you have to do is that you have to take an atom, you have to observe it under an electron microscope. How will you observe it? That is, you take an atom, means will an atom be visible? No. You have to take a particular what you can say, element. Clear? That you will observe it under a microscope. Then you will see the atoms, electrons, protons, whatever it is. You will be seeing the subatomic particles. Now, how will you see? Will you see in a dark room? No. Suppose you identify the position of an electron. Suppose an atom is there. Alright, let us say that pictorial representation I am showing you. This is the nucleus. We can say an atom is there. So electron, I have marked it here. That is A. When the light will fall upon it, listen carefully. When the light will fall upon it, the light is having sufficient energy to change the position of the electron, because electron will gain that energy. When the light will fall upon it, electron will gain that energy, and by gaining that energy, what will happen is that electron will change its position. It will acquire the energy. Just now I said you, it will acquire the energy and will change its position immediately. You will say, will not use the light. And how will you see it? How will you see then? Electron, protons, neutrons. How will you observe it under a microscope? Microscope, when you are observing it, light is required. Whichever light it is, sunlight, white light, whatever it is, light is required. And that light, when it will fall upon the subatomic particles, what will happen is that the subatomic particles is going to gain that energy, and immediately the electron will change its position. From here it may come back, it may come to this particular position. We can say that. Let us say B. So do you think the position here and the position here is the same? The path which is the same? We can say that? No. It's not the same, because angular velocity is changing. So momentum is going to change. Angular velocity changes, because angular velocity here and angular velocity here, is it the same? No. So momentum is going to change. So can you calculate the position as well as the momentum of a subatomic particle like electron simultaneously? Like in case of microscopic object, we are able to calculate it. I told you also an example. But in case of microscopic object like electrons, protons and all these things, the subatomic particles, are we able to calculate the position as well as the momentum? Because when you mark a particular position of an electron, you mark it that this is the position. When the light falls upon it, we see that particular electron there, but as soon as the light falls upon it, the electron changes its position. Because I said you why. Because electron is of negligible mass. The light is having sufficient amount of energy. The light is having that sufficient amount of energy to change the position of the electron from one place to another place. It is having. So you cannot calculate the position and momentum simultaneously. You cannot. Suppose you will say here I'll be in calculate. Okay, when the light will fall upon here, you will mark the position B, and when the light is going to fall upon here, then definitely electron will again change the position to C or somewhere else. It will move. It is going to jump from one shell to another shell by gaining energy. It is going to jump. It will change its position. So you cannot say, what you can say, the position of an electron. Now by this what we come to know, you know, Niels Bohr what he said, that in the first shell there is 2 electrons. In the second shell there is 8 electrons. In the third shell there is 18 electrons. He gave us a formula 2n square. So Niels Bohr actually was not able to experimentally find it out, this one. He assumed this particular one and he gave us a formula. Again I repeat, Niels Bohr did not give us this particular formula on the basis of experimental verification. It was his completely an assumption. Because when the light is going to fall upon it, the position of the electron is going to change. It will jump from the first shell to the second or third shell, we can say that. Then how can you say that in the first shell that 2 electrons are being present, in the second shell 8 electrons are being present, in the third shell maximum 18 electrons can be present? How can you say that? We cannot say with certainty. Can we say it certainty now? No, because the subatomic particles are so lighter, 9.1 in 10 to the power minus 31 kg, there is a mass of an electron. The mass of proton is 1.672 in 10 to the power minus 27 kg. It is so lighter, we can say that. So when the light is going to fall upon it, it will gain energy and it will jump from its position. Of course, protons is there inside the nucleus. We have nothing to do. We have to do with the electrons only. Alright? So, hence, what we find is that with certainty, we cannot say that the first shell contains 2, the second shell 8, the third shell 18. Maximum, I am saying, maximum capacity. We cannot say with certainty. But I am using the word certainty, we cannot say. So, hence, this principle is called as Heisenberg's uncertainty principle, because we cannot say with certainty. We cannot identify the position as well as momentum of an electron simultaneously. We cannot say. We will not be able to predict it. Suppose a rat is moving. If you allow a torchlight to fall upon the rat, if you focus a torchlight upon the rat, you will see that a rat changes its position. Yes, it changes its position. Why? Because out of fear it changes its position. Because somebody is coming to catch hold of it. It is not that the torchlight is falling upon it due to which it changes in position. No, not at all. Not at all. Suppose you are moving on the road. When the light falls upon it, does the position of that object changes? The macroscopic object like bus, or suppose you are only driving. When the light is falling upon it, is your position changing? No, not at all. Isn't it? So hence, what you find is that, or suppose you are standing. When the light falls upon it, is your position changing? No, not at all. So in this way, for macroscopic object, it is not true. Got it? So it is only true for microscopic object. Hence again I say, Heisenberg's uncertainty principle has nothing to do with the objects which we deal in our day-to-day life. I'll prove it also, this particular thing. It has nothing to do with those objects which you deal with the day-to-day life. And the subatomic particle which we are talking about, with certainty, we cannot say the position as well as the momentum of an electron simultaneously. Mind it, simultaneously we cannot say. Suppose we can calculate the velocity, a momentum of A, but the electron will not be at A. When you are calculating the momentum, the electron will be at B. Suppose you are calculating at B the position, then the electron will not be at B when the light falls upon it. It will be at C somewhere. So the momentum and the position you cannot calculate simultaneously. But for microscopic objects, we can calculate. No problem. We can do it. Clear? So understood? So hence this principle is said that Heisenberg's uncertainty principle, and the definition is also said that. What is the definition? Heisenberg's uncertainty principle. According to Heisenberg, we cannot simultaneously determine the position as well as the momentum of a subatomic particle like electrons. We can say, again I repeat, according to Heisenberg's, we cannot determine simultaneously the position, or it is impossible to determine the position or as well as the momentum of an electron, or of a subatomic particle like electron simultaneously. We are not able to determine it. Alright, so based upon this, he gave us a mathematical relationship. Heisenberg, what is that? He gave us is that delta x is the uncertainty in position, into delta p is uncertainty in momentum, is greater than or equal to h by 4 pi. H by 4 pi is a constant. Alright, he found it out experimentally, this one, that delta x into delta p is what? M into delta p. We can simplify this one. Delta x, again uncertainty in position, delta p is m into delta V is greater than or equal to h by 4 pi. We can say that. Clear? So delta V is uncertainty in velocity. We can say that. Uncertainty in velocity. Now one thing you need to remember here, that when I say we cannot determine the uncertainty in position, means what? Suppose if an electron is in the x-axis, if in the electron is in the x-axis, we cannot determine the position of an electron when the light falls upon it in the x-axis, because it will change its position. We can say that. Understood what I said? That is, it's important to understand that uncertainty principle, it is to the position and momentum along the same axis. Along the same axis, uncertainty in position and the momentum. Alright, what I said, if an electron is in the x-axis, you will see when the light falls upon it, it will not remain in that particular axis. It will change its path, it will change its axis. Clear? It's in the same axis we are talking to you. So in this way, Heisenberg's arrived to this particular principle that is known as Heisenberg's uncertainty principle, and based upon that he gave us this particular formula. Understood now? So hence what I said to you, that he challenged as a result the Bohr's atomic model. For that reason I said in the beginning that this is very important. We will be arriving up after reading this particular, what you can say, principle, we will be arriving to a new concept. A new concept will be arriving at. Alright, beginning, before that also I said it. Clear? So, what is that? What more, how can we prove it? This particular thing that it's applied only to microscopic object, not microscopic, we'll see it later on. Thank you.